Alright, so I'm doing an audio test here. Hopefully you can hear me. Alright, so I'm going to pull up a new window here and just make sure the audio is working before moving forward here. Take me a second. Play. Yep, alright, got sound, that's good. Alright, so here we go. Into this. All right, we're going to talk about water and solutions and a particular type of chemistry. And these really are the emphasis from chemistry that I'm going to be focusing on and what we're going to look to do with the chemistry that we have here. To recap what we just did and where we're going is we looked at where chemistry comes from an atomic level and how we classified elements. And the key driving force is the outer shells of electrons determine chemical reactions. And chemistry then is kind of cataloging all the different chemical reactions that can happen. What happens to the energy? Do you need to add energy to get a chemical reaction to go in one direction? Is energy released if it goes in another direction? How you can produce different materials or just different substances from letting these elements mix and create. So I don't want to focus on the particulars of it. I want the general idea that the outer electric shells of these atoms are coming together and binding. And through the reading material, you'll get some more specifics. But I actually want to focus on a very important localized thing, which is water. And solutions, dissolving chemicals into a liquid. We've hinted at that we are mainly made up of 6 elements. Biological processes are carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. That's 6 elements that make up biology. If you take into the earth has a little more iron and silicon. So a couple of those life processes are rare on the surface of the earth. But the thing we have a lot of is water. And water is kind of unique. It does some things that are physically unique that make life possible. And so discussing water in water chemistry talks about the chemistry of life. Inside your body, your cells are in a liquid blood that has some other chemicals in it. There are chemical reactions that are happening with water. You have solutions made with water in that are you. And those solutions in the chemistry drive what you do. You think in your chemistry you are mostly water on a planet that's mostly water, or at least the surface is covered mostly in water. And so this mostly water nature of this is important. And there are some things water does that is very, very, very unique. For example, all materials when they get colder shrink. They get smaller and smaller and smaller and smaller. And things when they get hotter expand. But water does this weird thing when it gets down to around 4 degrees Celsius. It actually starts to expand because of its shape, because of the shape of the molecule, and it's trying to get closer together right as it's about freezing. It kind of has like arms of hydrogen. The oxygen has arms of hydrogen, and the arms flatten, and that pushes the water a little bit further away, so it gets less dense. Which means when it turns to ice, the ice is actually less dense than the liquid. That's actually rare for compounds. And so this does something nice, and it does something amazing, actually, is that come winter months, water forms a protective layer of ice over its liquid part. And for many reasons, this actually keeps animals alive in the winter. If we lived on an alcohol-based life form with an alcohol-based planet, when it got cold enough for the alcohol to freeze, it would freeze from the bottom up and it would freeze completely away. And there would be no thermal barrier. And so organisms would freeze every winter and cease to exist. Or at least not be able to exist in a pattern here. So this uniqueness of water drives life, and it drives the shape of life and what life looks like. Well, the ability for water to dissolve things, it's called a universal solvent, means it can also harbor loads of various chemistries. And so we're going to look at the property of water because it is probably one of the most important things we have. It is a resource that is needed for life. Your very existence depends on water. And what's in your water affects your chemistry. So we can go from the micro level of this, of like, here's water, here's how water is dissolving salts, and how the ions in the salts would then react with other chemical reactions. You can also look at the macro level of this, that the things we do to our environment get dissolved in the water comes back to it, we have to drink the water, and it processes us. There's a micro and macro level to this chemistry. We live in a chemical planet that has large-scale chemical reactions going on that are also made up of many, many small chemical reactions. So I want us to appreciate the water and water solutions. And so I don't know why. Occasionally some slides are going to do some weird things, and we're just going to smile. This is one of them. So I'll read this out to you. Water is the most abundant liquid on Earth and is necessary for all life. Because water is great at dissolving properties, any sample contains other solids, liquids, and gases from the environment. So you look at a stream, and in that stream there are ground up rocks, right? In it, if you take a geology course, you'll study the ground up rock in it, and that rock actually floats. And the faster the water that moves, the easier it is for things to float on it. And the physics behind that are well known. Up here in Vermont, where I'm at, you can find places with very, very fast moving streams, because they come down the mountain very quickly, pull much larger rock down, and so that eroding of the rock pulls through. But that's floating in the water, and that's a mixture. Other parts of it, the salts and the crystals in the rock, can dissolve, and that's going to be what we call a solution. And so we're going to look at solutions. So a solution is a homogeneous mixture of ions or molecules of two or more substances. So notice it's a mixture, but it's a mixture of ions or other molecules from two or more substances. The solution you know the most is salt water. You can go into your kitchen right now, you take a tablespoon of salt, you plop it into a glass of water, stir it. That water is no longer what it was before. It's a solution of salt and water. And what happens is sodium and chlorine make up the salt. In the water, it breaks apart into two ions. The water rips apart the solid. And now you have ions of sodium and chlorine. But it doesn't release deadly chlorine gas. It's an ion. And in the solution, it's acting as if the salt's kind of sort of solid, right? It has broken them apart, but it hasn't turned them into base elements. And so by being trapped in the water, certain properties of it are manifest. Same thing happens, you put a little salt on your tongue. Your tongue dissolves it, and your tongue's actually experiencing the sodium and the chlorine ions. All right, and so there are two parts. There's a solvent, which is the component that is in the largest quantity. The solvent. Then there's the solute, which is the thing that gets dissolved into the solvent. So again, going back to the salt water, the water is the solvent, the solute is the salt. If one of the components of the solution is a liquid, it is usually the solvent. Because the nature of a liquid, it can flow around things, it can surround things. And so it has this ability to actually surround something, rip it apart, and dissolve it. Notice the word solvent is in there. Dissolve, solvent, solute, solution. We have our root here. If the solvent is water, then the solution is identified as an aqueous solution, a water solution. And so we're going to be looking at water solutions merely because they are fundamental to our idea of living. And they are the things that give and dictate basically life and are the nature of life. Well, it's important to me. All right, so, but that doesn't mean that liquid or aqueous solutions are the only thing, right? And so they're looking at a city and they're saying, hey, there's at least three kinds of solutions here. There's gas and gas oxygen dissolved in nitrogen. There's liquid in gas water vapor dissolved in the air. And then there's solids, which are tiny particles of smoke dissolved in the air. So the solvent is the air. And because our air is mainly nitrogen, we're going to say nitrogen is the larger component of that. And then oxygen is dissolved in that nitrogen solvent. Now that new solution of nitrogen and oxygen also has water vapor dissolved in it. And it also has particulate matter in it. And so the solution has different components that we can look at chemically differently depending on what we're doing. And we can have a gas, not a liquid, doing the dissolving. How we define solutions is the concentration, right? You can go into your kitchen, you can put a tablespoon of salt in the water, you can stir it up, and all the salt vanishes. And you can keep adding salt in until it stops vanishing when you stir it up. But the amount of the salt going in the water increases. It gets more concentrated. There's more salt and less to the overall volume than water as we go through. There's more salt getting put in there as you add more in. And so concentration is a way of measuring of how much of the solute is in the solvent. And the concentration of the solution describes the relevant amounts of the solute in the solvent. Concentration solutions contain large amounts of solute. So we use the word concentrated, right? You get a large amount of the stuff in there. I think that word sometimes gets, because from industrialized food, we would remove the solvent out of things and say it was concentrated, right? And you just add a water. I remember as a kid, the frozen orange juice was the thing we always used to got, the concentrated orange juice, where they would take a gallon of orange juice and remove all the water or most of the water and then freeze the result, and then you would plop it into a jug and pour water into it to have orange juice. Dilute solutions contain little solute. So we're going to have two words. If you dilute something, you add more of the solvent so that less of the solute is in it. Right? And I think we use that word fairly well. We dilute things, and diluting them brings down the amounts in them. And concentrated, there is more. And so there are different ways to talk about this. We can talk about parts per million or parts per billion. So very toxic things, we can talk about parts per billion. And then we can say percent by volume. Percent by volume. And we also talk about molarity. Now, molarity is great for chemistry because moles count the number of atoms of things. And so if we know how many moles there are per liter of solution, we know the driving number of atoms in chemical reactions. And so molarity is the good way to talk in chemistry. But when we're talking about like environmental conflicts, contamination, if we're talking about other ways of measuring it, parts per million and parts per billion tend to be a really good comparison, especially for airs and gases. Molarity tends to drive chemistry, and percent by volume, I think, is the general term that kind of sits in the middle that gets used a lot. But the same idea is that we're looking at some way of measuring the amount of solute per solvent. And so here we look at an example of doing this. So the upper graph says as parts per million / parts per hundred. slash parts per whatever. It says, hey, there's 2 parts of the solute and there's 98 parts of the solvent. So it's 2 per 100 in the solution, right? And then if we have 2 volume units of the solute and 98 volume units, we have 100 volume of the solution, that's a 2%. And then the last one as a percent of weight. Now, again, I hope you see that I have a theme here, and the theme here is all of these things of physical science become the backbone of biological science. It's the environment that biology exists in. And we talk about life coming from the oceans. Salt water and salinity is a good measure. And so salinity is a thing that's specifically talked about. Salt water, you can't drink as fresh water up to a certain level of salinity. We even have a word for water that's too salty to drink. It's brackish, right? And so salinity is a measure of that. And salinity is the measure of amounts of salt dissolved in a kilogram of solution. So if 1,000 grams of seawater were evaporated, you would get 35 grams of salts remaining. And that would leave 965 grams of water. And so the salinity is a measure of how much salt is in the water. And yes, you can evaporate it out to get it back out. So when we talk about different materials, we want to talk about how we can get those materials to dissolve. And that's going to be called solubility. A saturated solution is an equilibrium mixture that exists between solute and solvent, where the rate of dissolving is the rate at which the solute is coming out of the solution. So when I saturate a solution, any bit that I dissolve will be matched with an equal amount that's precipitating out. So if you go back to I take a tablespoon and I take a salt, I keep adding salt into water and stirring it up. Eventually, every time it goes to dissolve some of the salt also has to re-solidify. Because it's a two-way chemical reaction. This thing is going in both directions all the time. But there's enough, if you have enough solute, right? So imagine one tiny, tiny grain of salt in a jug of water, and it breaks down into its ions. Those ions want to come back together and form the salt. And so they do, but they're in this huge jug of water, so they break back down again. And so they never truly stay together. But if I fill it with ions, and ions are constantly forming back into a salt, they don't have the room to stay apart. And that's what this is saying. It is in this liquid, everything's trying to come back together and be dissolved, and I can reach a saturated state. We call it saturated. And we can there'll be this thing called supersaturation, where if we heat the water up, we might be able to dissolve a little bit more and then cool it down right to the rate where it doesn't do anything. In fact, we form crystals a lot this way. We'll dissolve more than what a liquid can take by using a supersaturation, and then we'll disturb it or give it a string, right? You can make rock candy this way. You can dissolve sugar in water, and if you heat it up, you can dissolve more sugar in the water than what it would have cool. If you drop a string in it, that sugar will reform around the string or a stick, and you can make rock candy that way. You can form the sugar into the shape around what you put into it. So this ability to dissolve, and the things that we're dissolving wanting to come back out, we can chemically use to make things happen. And so solubility is the concentration of a solute that can be dissolved to make solutions at a given temperature. Notice temperature is important. How things mix is related to energy, and temperature is the average form of energy. And so by increasing or decreasing the temperature, we can add more energy to break things apart more. Right? There's a breaking process going on here. And so we have to note that solubility changes with temperature. And we play with that trick to let solubility make things for us. And most things will be able to dissolve more readily at higher temperatures, while gases get harder to dissolve at increasing temperature. And that's because the gases get further and further away. And so here are some solubility curves for sodium nitrate, potassium chloride, and sodium chloride. They are different salts. Sodium chloride is the table salt, and it's fairly even for temperature. Potassium chloride, which I think is actually used in some sidewalk salt now, so as to be slightly safer than sodium. Less polluting because you'll get potassium out instead of the sodium chloride. But it dissolves a lot more easily over temperature. But at colder temperatures, it doesn't dissolve so well, right? All right. So we want to look at water solutions. And so we're going to look at what tetrahedron, which is a four-sided pyramid. For the D&D players, it's your four-sided die, right? Molecules with four bonding electron pairs have this shape. And so they've illustrated the CCI4 molecule, this carbon iodine molecule. So it's a CI4. I don't know why the C was repeated. The carbon atom is in the center of the pyramid, and the chlorine atoms make the four corners. They fall apart. A water molecule has two bonding pairs, and so it makes this kind of flat tetrahedron, right, with a 105-degree angle. So it's showing a carbon iodine pattern here, and then it's showing a water molecule here. And so the properties of this is water is a polar molecule. The oxygen has more electrons in its outer shell than the hydrogen, and so the oxygen has this. Let me get it here. That's my oxygen, and these are my hydrogens. That has a really large negative charge, and this is a very small positive charge. So all the electrons are in towards the center there, and because it has that shape and the hydrogen sticking out on the outside, we have a positive charge over on the side that the hydrogens are on. I always thought a water molecule, when you do a good molecule diagram of it, looks like a Mickey Mouse. But don't let Disney sue me. Sorry. They sue everyone. No, they don't. They're not using any of their songs. We're good. So we say this is polar because there is a noticeable difference in electric charge. The electrons spend more time around the oxygen, giving the oxygen side a negative charge, and the hydrogen side has a positive charge. This charge difference allows water to dissolve things, because what will happen is the negative stuff will attract positive things to it, and the positive side will attract negative things to it. So if we have something that could easily be broken into ions, the water's going, I've got two sides! Yay, all your negative stuff, come over to my positive side. All your positive stuff, my negative, and it just starts ripping apart things as it comes through. This difference in charge lets the water start ripping things apart. And this sets up intermolecular forces. And this is what I just said here. And these are called van der Waals forces because they happen on a small scale. And compared to some other forces we'll get, they're not that strong. Now, inside of the hydrogen in the water molecule, the hydrogen atom and the oxygen atom has this thing called a hydrogen bond. That bond is fairly strong compared to, well, how do I want to say it? Hydrogen is a weak bond between a partial positive hydrogen and a partial negative. It's a weak bond compared to like other bonds. In a comparison force, the hydrogen bond is not going to be broken apart by the interaction with the ions. So the ion bonds that the van der Waals force is breaking apart is weaker than the hydrogen bond of the hydrogen and the oxygen. Now, overall in chemistry, hydrogen bonds are weak. But in these chemical processes and these positive and negative charges are ripping things apart, they're not going to rip apart the water molecules. Right? So it's going to say, hey, this is a weak bond. It's weak chemically. It's a weak chemical bond. But compared to the ions that we're now ripping across, the ionic bonds we're ripping across, and the forces due to these charges, the water molecule is going to stay intact. The ions that are in the water molecule are not. And the attraction between the two different sides pulls the water molecules together. And we talked about this a bit before when we talked about the phases of matter and how we form ice and how the arrangement of ice comes through. And this is what I was talking about. The density of ice goes down right around 4 degrees. Or water goes down around 4 degrees, which means that ice is less dense. All right, what I want to talk about is the mechanics of how things dissolve. There's a limit to the solubility of any molecule in a solution. Some substances do not dissolve in a solution, like oil and water. And fluids that can mix freely with each other are called miscible. And fluids that cannot mix freely are immiscible. And that's the oil and water. And so there's something about the structure of different things that make different properties. And so we will get this list of properties that make different chemistries, different solutions. So water is polar and carbon tetrachloride is nonpolar. Since like dissolves like, water and carbon tetrachloride are immersible. So polar substances will dissolve better. That's what the like dissolves like means here. Soap works really well in cleaning grease because a soap molecule is two-sided. One side, the hydrocarbon end, is soluble in oil. The ionic end with the, over here, here's the hydrocarbon end. Yeah, that dissolves in oil. And then over here, this ionic end, which has this positive sodium ion, is soluble in water. And so this two-sided nature of soap lets it have the best of both worlds. And that's why you put soap in water and it'll help break down the grease or the degreaser. And so it's a link that makes it'll wrap itself around the oil, and the side that's soluble in oil surrounds it, and the side that's soluble in water then lifts away. And so it's one side is breaking apart the oil, and the other side is dissolving in water. And as it breaks apart the oil, it surrounds it. And so this chemistry, these reactions, are little machines. This thing here is a machine. This side of the machine acts differently than this side of the machine. And when this side of the machine finds oil, it dissolves into the oil. And a whole bunch of these come together and they cover the oil. But this side is soluble in water, so now this oil is surrounded by something that can dissolve in water. And so the chemical reaction, these properties of these electromagnetic forces on this molecular scale create a machine that can surround our piece of dirt and then make it so what has been surrounded can wash away. And so ionics dissolve in water because the water molecules go around the surface, and there's more of them, and the polar water molecules pull at the ions, and they pull at the ions, and they pull at the ions. And so the water flows around it. It's polar, it's positive and negatives dance around, and the positive side of the water molecule goes to the negative side of your crystal and says, hey, come over here. And because they're around and flowing, these add up to lots of tugging and pulling, while the ionic crystal itself is balanced. And so very locally it's polar, but overall it's neutral. And so overall it doesn't have a net force. And then on its local side, all of this water's tugging at its little local bits. And so it breaks it down. And there are some things you can do knowing this. that make things dissolve faster, right? So notice the water has to cover the ionic compound. And so if you want things to cover more of something, you need more surface area. And so if I am dissolving a salt, the best way to do that is not to just put the salt in the water, but it's to crush it, right? And so if you take like a cube of sugar versus that sugar crushed up, cube of sugar takes longer to dissolve than it crushed up into its grains. The amount of surface area that can touch the solvent increases the rate of I just lost the word. the rate of dissolution, I guess, would be the best word. And so there are some properties that we will get from solutions. Why these things matter, why they drive chemistry. So they're electrolytes, right? That's what plants crave, right? Why Rondo? Rondo has electrolytes. That's what plants crave. If I dissolve an ion into an aqueous solution, right? If I dissolve salts into Gatorade, it creates different charges in the solution. And since there's a charge in there, electricity can flow. Right? This is, making a lemon juice battery. Well, that's actually slightly acidic. Salt water conducts electricity better than neutral water because of the ions in it. The ions have charge and the ions can flow. A solution which can conduct an electrical charge is called an electrolyte. A solution which cannot do that is a non-electrolyte. So if your solution is not ionic, it's not giving positive and negative charges, it won't conduct electricity. If it does have positive and negative charges, it will conduct electricity. Ionic compounds ionize in water to form their individual charged particles. Acids create a hydronium ion. And so this is an example of what you can do with this. It would be really, really nice if I knew everyone could get out to Radio Shack, because for less than $5 you could do a nice little experiment like this, where you could take a 9-volt battery and a small pen light lamp, and you can try different solutions and stuff in the kitchen, just to see how this works. I'll see if I can find a video, and I'll try to post it with the videos here. We'll go. Wait, I might actually have a pen light lamp. Oh, no. I'll search through my stuff to see if I can do this. But that would be the difference: is if you can make the current flow through the water, you have electrolytes, and if you can't, it's non-electrolytic. And electric flow is important, like your neurons. And so the idea of having electrolytes now is something you need. And the ideas of Pedialytes and Gatorades are the realization that we actually need to keep an ion flow in our water chemistry to keep our biological processes that use electricity and magnetism to work. And so here are 3 representations of water and hydrogen chloride in an ionizing reaction. So in the first one, it shows the water plus the hydrogen chloride, and when it comes out, you have 3 hydrogen atoms around the oxygen, the hydronium ion plus the chlorine ion. The electric dot notation shows the same thing as the upper picture, right? So here it's showing it as the Mickey Mouse ears, right? Interacting with this hydrogen gets attracted to here, and when it does so, it gets ripped away from the chlorine. Here, this is the same thing in dot notation. And so this hydrogen fills this one empty spot in the hydronium ion, and the chlorine's over here. And this hydrogen has this extra spot. This is why hydrogen chloride, this hydronium ion is useful. And then here it is in in a chemical equation, noting that these are ions. Now, and these are just symbols to talk about the process that's running underneath it all. The boiling point of a solution is the point at which enough energy has added to overcome the molecular forces that hold the solute in the solution. Water has a known boiling point. If you put salt into it, though, it changes. And so the boiling point in general, we're talking about the solute being held in the solution. Once this point is reached, the solution vaporizes and becomes a gas. And freezing point is the opposite. All right. I actually want to comment on this. Is we do use this, right? When you're putting salt into something to boil it, you're changing the temperature at which it boils. You're letting it take more heat and have a higher temperature. And that's actually a temperature control. It's not just for flavor. And so when you see like pasta directions needing a certain amount of salt to go with the water, you're using it as a temperature control to change your boiling point. Because once you reach the boiling point, you actually can't get the temperature to increase in the liquid because it's escaping away as a gas or as a vapor. And so by using this solution, you can change boiling points and get a temperature control out of this. And so that's what this is saying. It's saying the rate of evaporation stopped on the wrong slide. I wanted to stop on this side. I'm like, why is it doing this on this side? The rate of evaporation unless the vapor pressure is less for a solution than for a solvent. The greater the solute concentration, the less the vapor pressure. That means you need a higher temperature for a salt to go through. So by adding salt to pasta, you're cooking your pasta at a higher temperature than boiling water would do. And that makes the pasta cook to a tenderness more quickly and more appropriately. You get the salt level wrong and you don't. And you also we get a side effect of flavor. Same thing happens with the freezing point. Energy changes. All right. Last thing we're going to cover here, like I said, this wouldn't be as long because the audio actually worked, is the idea of acids and bases. And so these are solutions that have different chemical properties. And we're going to talk about these hydronium ions again and this particular molecule of hydrogen and oxygen that breaks apart other molecules. And there's a scale for these, and acids and bases are kind of two ends of a spectrum. Water is in the middle of that. And so the property of acids are they're sour to the taste. I'm drinking lemonade and thinking of that. There is a test paper that they changed from blue to red. They react with metals to release hydrogen gases. So you put a metal in an acid and it releases hydrogen gas. And they neutralize bases, and when they neutralize a base, the salts come out and water comes out. The bases they're bitter to taste, right? Bases turn red litmus paper blue. And they feel slippery to the skin. They feel soapy. And they neutralize with acids forming water and salt. And here's an example of litmus paper testing if it's a base or an acid. And two household acids and bases are vinegar and baking soda. Your baking soda volcano is an acid and base reaction, and it's neutralizing. And it's a neutralizing reaction, and you get a gas released from the baking soda, and you get a water out of it. All right, acid-base properties are explained looking at how they ionize water. When you reach an equilibrium point, the two reactions happen at the same time. It's not that the reactions stop. Equilibrium isn't saying that the reactions stop. You think of it as a revolving door, and your chemical reactions are people going in and out of the revolving door. And when the people going in and out are going at the same time, always they're in equilibrium. So you never get more people inside or outside because they're going through the door at the same rate. When you have more people outside, if you have more of an acid and you're going towards the base side, they'll go through the revolving door, and eventually when you have equal amount of people on either side, they'll keep flowing through at the same rate. And that's what the chemical reaction does, is it balances out so that the rate that it's dissolving is equal to the rate that it's creating. And so the acids and base equilibriums aren't that it has stopped, it's just it's happening at exactly the same rate, so you don't notice a change. And here is an example of a chemical reaction where water, negative water plus an ionized water plus H2O produces hydronium ions. And this reaction can occur in both directions. And so the reaction is going backwards and forwards until it balances. And what we kind of say is an acid donates a proton. And a proton is a hydrogen atom without an electron. So we can say it donates a positive ion, positive hydrogen ion. And a base is a proton acceptor. It takes that. And so there are different strengths to that. Strong acids ionize completely in water. You put a strong acid in water and it breaks down completely. Weak acids only do this partially. Strong bases ionize completely in water, and weak bases only ionize partially in it. Hydrochloric acid or muriatic acid is a strong acid, and it's used because it is a strong acid. It breaks apart bases fairly well, so it's used to destroy organics, hence in the swimming. And it's used to dissolve other things. Right. All right, so to measure how strong things are, right? If we want to know what's strong or weak, we look at a pH scale. Right? And I actually kind of like, thinking about it now, muriatic acid in the swimming pool, because you're using it to kill bacteria in it. You want a strong acid. What you end up trying to do is you try to get a good pH scale that your pool isn't dissolving you, but it's keeping the algae from growing. And that's the acid strength, and it's measured relative to how much of the positive and negative concentrations are in the water, in the solution. Since the ions are breaking apart the solute into H3O positive and OH negative, you want to know the relative amounts of these. And so acidic solutions have concentrations of H3O plus above 1 times 10 to the negative 7th. So it's a small concentration, but it's above that. Notice the 10 to the negative 7. The negative 7 is really important here. And we're above 10 to the negative 7. Neutral solutions have concentrations about 10 to the negative 7. Again, note the negative 7. That's the important number. Basic solutions are less than 10 to the negative 7. And so what they've done is they've made a pH scale. And it's a per hydronium. It's a measuring how much of this stuff we have. 7 is the middle of the scale. And the 7 comes from the 10 to the negative 7th. And so what the pH scale is doing is it's actually keeping track of what the negative 7 number is. So a pH above 7, let's say I have a pH of 8. If I have a pH of 8, I'll write this down here, up here. If I have a pH of 8, then in my concentration is 1 times 10 to the negative 8. which is less. And so that's more basic. If I have a pH of 5, I have 1 times 10 to the negative fifth, which is more, and that's acidic. And so what we end up with, which is a scale from 1 to roughly 14, where this is very, very highly acidic. This is very highly basic. And 7 is neutral. So instead of having to talk about 1 times 10 to the negative 7th and stop and think, what is 10 to the negative 7th? That's 6 zeros after the decimal place. It's a really small number. What we can do is we go, okay, it's 1 to 14. 7's neutral. 1's really acidic. 14's really basic. And so each division is an increasing power of 10. And here we put this scale out, right? If you're neutral, you're 1 times 10 to the negative 7th. As you get lower, you get more acidic. And as you get higher, you get more basic. And so pH increases as the acidic strength of these substances decreases. Right? Lemon juice is more acidic than Donald Duck concentrated orange juice. I wonder if that's why I was thinking of concentrated orange juice, because they're putting the slides together. I haven't seen that stuff in ages. I don't even know if it's still sold in the stores. Yeah, maybe the next time I wander out to the store, I'll see if I can get Donald Duck. I just remember having freezers full of that. All right. So when we put an acid and base together, they will produce salts. A salt is an ionic compound except for the hydroxide and oxides. Because those hydroxides and oxides are part of the acids and bases. And a solution can contain ions because it's called hard water because it interferes with the ability of soap. And so what we're talking about is things dissolved in our liquids. How these things get dissolved in our liquids. Right. And so here, if we look at everything we're looking at, we're talking about chemistry happening and the ability of solutions to happen. I kind of want to tie all this together in the last 5 minutes here. As I said, I was only going to do about an hour of this. I was going to do 2 1-hour bits, a little bit longer in the other bit because the sound died and I had to redo the 20 minutes. And so I want to kind of wrap this up here is that water is a solvent. It's dissolving other things, making solutions. And it's doing this because of the shape of the water molecule and how the electric charge is distributed from it. And it's pulling apart ions. And then we look at other solutions, if they're acidic or basic, which tells their strength of how they create our hydroxides and oxides, or our hydronium ions. And that does the nature of the water we have. And so there's this chemistry that's happening due to the geometric shape of our water molecule and how that moves electric charge in space. And that electric charge is used to rip apart other things. And now we have ions in water, and we have acids and bases, and they dissolve things or they neutralize things. When neutralization comes out, we get these salts. And so this book's right now looking at the idea of, well, we drink water. And sometimes we have hard water, right? Soap doesn't dissolve in it well. Well, why isn't it dissolving in it well? Well, it has other ions in it. Where are those other ions coming from? Well, it's coming from rock, right? And sometimes you have scaling in water. And so the water is working its way through its environment, dissolving things as it goes through. And some of that dissolution process will cause issues with the nature and quality of the water you have. I'm sorry, I keep moving my mouse and it keeps jumping over some slides here. And a water softener system is a way of taking out those excess ions so that it can dissolve soap better. But the water that you have is doing this job as dissolving things, and in doing that, it ends up with components that affect its chemistry. And so that's the things we have to manage, from hard to soft water to the biological components it can keep into it, to the pollutants it can keep in. And so this chemistry nature of water and water's ability to dissolve things helps make life possible. But at the same time, it has issues to deal with the water that we have. And I'm going to skip buffers because the buffers is the last thing here. I really wanted to wrap up on the idea of the concept of water coming back through. So these two parts in chemistry, what I wanted to look at was the nature of how we classify things chemically, and how the elements are forming chemical reactions based off of their outer electrical shells. And those outer electrical shells and electricity, the electric charge, is the driving force of chemistry. It moves the energy about. In the second part, we wanted to look at dissolving things, and specifically water. And dissolving is the ability of certain molecules to rip apart other molecules and other compounds and break them into ions, or break them into non-ionic components. Most of that ripping apart comes from the shape of the molecule. And so when we looked at soap with its large shape but two distinct different ends, it could dissolve on one side oil, and on the other side it could be dissolved in water. And so in doing that, it would surround the oil, and then it itself would dissolve into the water. And that's how soap works. And so these atoms aligning themselves make these machines. And really wanted to overall emphasis in this ability to dissolve and having solvents and solutes, making solutions, was water, because water is so dominant. And so we talked about how you can make acids and bases, what was the scale for an acid and base, and how they could help dissolve things, and how they would react with each other to create salts. The underlying drive of all of this is the shape of the water molecule, and which is prevalent in everything. And the thing really to reflect upon is that if I'm standing on my front porch, I see there's a stream just out of view, but I can see all the trees around the bank, and if I were to open the windows, I could hear it. And that water is coming down off the mountains I see in the background. And as it comes down off those mountains, it dissolves bits and pieces of the rock. It interacts and becomes the chemistry that works with all the plant life coming through. It drives the chemistry of all the life around. And the things that it's dissolving and carrying, it becomes a carrier for chemistry. And life flocked to it to get this ability to break apart material to use it. And so life kind of has to do this weird thing. It has to break apart things to use their components, and it has to put them together into complex forms. And because water's shape lets it do this dissolving, water is a universal solvent, an ideal mechanism for life to get whatever resource it finds useful. In a modern context, that also means all the waste and all of the toxicity. Well, water doesn't discriminate, and it's going to carry that about, and it's going to move that about. And these are the things we have to think about as we look at the chemistry on its micro level and the macro level that we have. All right, that's everything I have for the chemistry section. I'll be posting the readings up for the astronomy section. If you need anything, email me. You're allowed to ask questions in chat while these things are going. I know I'm recording them for further review, but fire out any questions that you have. And I will be doing the astronomy ones starting on Friday. I'm definitely going to do the 12 to 3, 2:30ish 3. We're going to take a small break in the middle. All right. Have a wonderful one. Be safe. Be well.